In this video, let us derive D'Alembert's principle. Jean-Laurent D'Alembert was a French mathematician, musician, mechanician, philosopher, and physician. He has done so much to physics, especially in the field of fluid dynamics, mechanics, and so on. Apart from this, he has also co-edited the world famous encyclopedia. With this little introduction about him, let us derive D'Alembert's principle. D'Alembert's principle is almost similar to, or it represents Newton's second law of motion in a different way or another way. He gave his principle based on principle of virtual work. We all know the principle of virtual work is only applicable to explain the statics of a system of a particle. To explain a system of particle which are in a motion, we need a new principle. So, to describe the dynamics of a system of a particle, we make use of D'Alembert's principle. Whenever we talk of moving particle, we talk of Newton's second law of motion. So, by Newton's second law of motion, we all know the force is defined as rate of change of momentum. So, F is equal to dP by dt. For the ith particle, it is Fi is equal to Pi dot. So, in classical mechanics, we all know one-time differential is written as an dot. So, dpi by dt is Pi dot. Now, let us take this Pi dot to the left hand side. We get Fi minus Pi dot equal to 0. Let us take this equation as equation number 1. Okay. Now, we can say a moving system of particle is in equilibrium under a force Fi minus Pi dot. That means to keep a moving system under an equilibrium position, a force of Fi minus Pi dot has to be acted on that system. Here, this Fi is called as the actual applied real force, and minus Pi dot is called as reversed effective force acting on the ith particle. So this was the force which was introduced by D'Alembert to keep the moving system of particle under equilibrium. So minus Pi dot reversed effective force acting on the ith particle. I have already introduced that this principle is based on principle of virtual work. So we make use of this principle of virtual work. The mathematical representation is summed over I Fi into delta Ri equal to 0. We know the Fi is the force acting on the ith particle. Delta Ri is the virtual displacement the system makes in a small time. So in place of the force Fi, we can write the force here Fi minus Pi dot into delta Ri equal to 0. But this capital Fi is equal to Fi of A plus small fi. So this Fi of A is nothing but it is an applied force acting on the ith particle, and small fi is called forces of constraints on the system. So putting this capital Fi in equation 2, we get summed over I Fi of A plus small fi, the forces of constraint, minus Pi dot into delta Ri equal to 0. Now, in this, we are rewriting this equation by taking the Fi from that and writing it at the end. So, the equation becomes summation Fi of A minus Pi dot into delta Ri plus summation small fi delta Ri equal to 0. By the principle of virtual work, we know the forces of constraints do not do any work on the system. So, we can say the product of Fi into delta Ri, that is summed over I small fi, the forces of constraint, into delta Ri equal to 0. So, this represents the work done by the forces of constraints. So, we all know the work is given by force into displacement. So, small fi into delta Ri is the work done by the forces of constraint, which is equal to 0. Let us put this in equation 3. So, equation 3 becomes summed over I fi of A minus Pi dot into delta Ri equal to 0. Henceforth, we are not going to mention anywhere about the forces of constraints. So, we can drop the superscript A in equation 5 in the fourth term, which makes equation 5 as summed over I Fi minus Pi dot into delta Ri equal to 0. This equation is called as D'Alembert's principle.